Welcome everyone. For our first prep video, we're going to introduce the idea of limits, and we're going to do this graphically. So we're going to see, by the end of this set of notes, how to estimate the limit of a function using graphical methods. All right, so first I want to introduce, or not really introduce, but just kind of recall, how do we actually read the graph of a function? So we're going to look at this example. We're given this graph y equal to g of x, and we're going to evaluate this function at a few different x values. So we're going to evaluate g of 1, g of 4, and then g of 2. Okay. So, and we see the graph of our function over here. So let's start with the first one. And the number inside the parentheses here, this tells us what the input, what we're actually plugging into our function. So in this case, the input is x equals 1. So that's what this one here is. All right, so how do we read the graph? Well, we find x equals 1 along our x-axis, and then from that x value, we look up or down until we see the corresponding point on the graph. So we read up, and there we go. We've got our point. So let's just kind of fill that point in. We'll just enlarge it so that we can actually see it there. All right, so we've got our point on our graph at x equals 1. And, let's think about what are the coordinates, what are the geometric coordinates for this point? So we know the x coordinate is 1. What is the y coordinate? Well, the y coordinate, if we look over, we're not quite all the way up to 1. We're a little bit higher than halfway up. So, I might estimate this to be 0.8. Seems reasonable there. So whenever we read a graph, we're really just estimating, trying our best to kind of read between the lines there. So 0.8, maybe you say 0.75, sure. All right, so our x-coordinate is 1, our y-coordinate is 0.8. So that means the output of our function here, in this case, what is the value of g of 1? The output is the y-coordinate. So our output is 0.8. So the input is the x-coordinate, the output is the y-coordinate. So that's kind of a helpful thing to remember. Whenever we're talking about a function, g of x is the y-coordinate. So whenever we write down a function, normally we write it like y equal to g of x. So we've got the x-coordinate is our input. And the y-coordinate is our output. Okay, so with that in mind, let's think about what happens when we plug x equals 4 into this function. So again, we go back, we find 4 on our x-axis. There it is. And then, we look up or down until we see the corresponding point on the graph. So we go up, 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 and then we see our point on the graph. So for the second point, let's try to interpret what are the actual geometric coordinates for this point. So the x-coordinate is 4. What is the y-coordinate? So we look over, and to me this looks pretty close to halfway in between the 2 and the 3. So I might say 2.5. So the input is the x-coordinate. The output of our function is the y-coordinate. So we would say in this case that g of 4 is equal to 2.5. All right, so what about the last one, g of 2? So let's look at this. So, we find x equals 2, find the x value, our input, along the x-axis, and we read up or down until we see a point on the graph. And what we see here at x equals 2 is these open dots. And this is a way that we kind of graphically indicate that those points are kind of missing on the actual graph of our function. So when we graph a function, if we use a filled in point, so if we have this enlarged point and it's all filled in, that means it's included in the graph. If we have an open point, so an open dot like this, that means that that point is actually missing. It's excluded. It's not part of the graph of our function. And that's what we're seeing here, is this point, we've just kind of enlarged it to show the detail here, but this point is missing. Same with this one. This one's missing as well. It's not actually part of our graph. So you can think of when we draw the curve, generally we draw these functions and lines with kind of one clean motion. But the way you can think of these is when we graph a function, what we're doing is we're just plotting a whole bunch of filled in points, and all those filled in points just kind of blend together to give us the illusion of this kind of, well, in this case, a line segment. But really, these are all just these filled in points, and we've just plotted enough of them so that they just kind of blur together to give us what looks like a line segment there. And then we get to this endpoint, and it's missing, so we leave it as this open dot. So at x equals 2, this one's kind of a trick question. If we look, there's no actual filled in point at x equals 2. No matter how far I go up or down there, there's no filled in point. So we would say this function value does not exist, or it's undefined. All right, so that's reading a graph. Now we're going to introduce one-sided limits here. So similar graph, not exactly the same function, because in this function here, we see that one of these points is actually filled in. So this function is actually defined at x equals 2. So technically it's a different function. All right, so what we're going to do here is we're going to start investigating the idea of one-sided limits. And to do this, we're going to look right around x equals 2. We can kind of see something interesting is going around to this function around x equals 2. It's kind of like a break in the graph there. And what we're going to do is we're going to say, all right, well, let's kind of step away from 2 exactly. And we're going to look a little bit on the left, and we'll look a little bit on the right. So let's start on our left side. So if x equals 2 is kind of where we're investigating, this is kind of where we're interested in, the left side of that would be right over here. And so the idea, or the question we want to answer, is what geometric point does the left side of our curve approach near x equals 2? All right, so we're interested in x equals 2. We're going to take a step away, so we're going to go to the left side here, and we're going to imagine a little person. Imagine we're going to walk along this curve, and we're going to see where the path takes us. And it looks like if we follow the curve here, if we follow this, the graph of this function, it looks like we're going to be walking closer and closer to this point. So on the left side, as we walk along the path, we're getting closer and closer to this point. Now, you can think of this, because this point's not included, you can think of it like the edge of a cliff. So, we're getting closer and closer to the edge of a cliff, but we're not actually going to take that last step over the edge. So we're walking closer and closer, but we don't actually reach that specific point. In this case, that's missing from the graph of our function. But we're still kind of headed in that direction. So what is the coordinates at this point? So the coordinate for that point, the x-coordinate is 2, and the y-coordinate to me looks to be about 1. So on the left side of our graph, as we walk along our curve from the left side, and as our x values are getting closer and closer to 2, it looks like we're walking closer and closer to this point here. Okay. So what about the right side? So again, we're interested in what's going on right around x equals 2, but now we're going to move over to the other side, to the right side. So now we're in this realm over here. And again, we want to imagine kind of walking on our curve, and we're just going to see, where does this path take us? And as we take our steps, we're moving closer and closer. It looks like we're getting closer and closer to that point. So what is the coordinates for that point as we're moving closer and closer? Well, to me it looks 2, 2. The x-coordinate is 2, and the y-coordinate is 2. So it looks like we're heading closer and closer to that point. Okay. So what we have here is the left side of our graph looks like we're headed to kind of this point. The right side of our graph, it looks like we're headed to another point. And we want to be able to kind of mathematically describe this behavior. And the terminology, the notation that we're going to use is left side limits and right side limits. So our left side limit, the notation that we use is we use LIM for limit, and then we have our function, so f of x. And the way we read this is the limit of our function f of x as x approaches a. And we have this little minus sign here, and that's to indicate that we're getting closer and closer to a, but we're a little bit smaller, we're a little bit less. So the minus sign here is for our left-hand limit. And for our right-hand limit, it's very similar notation. So LIM for limit, we have our function f of x, and we're seeing what happens as our input x gets closer and closer to the number a, but we're using values that are slightly bigger, so we've added on a little bit extra to the input. So the right side uses bigger values, and the left side limit uses smaller values for our kind of our inputs. So what we would say in this case, going back up to our example here, what we would say is that the left-hand limit, so how would this look? Well, the left-hand limit of our function, so x is going to approach 2, and for left-hand limit, we use a little minus sign. So we're using, over on the left here, we're using values that are a little bit smaller than 2. So subtract a little bit. And so the left-hand limit is the y-coordinate. So what is the y-coordinate of that point that we're approaching? The y-coordinate there is 1. So we would say our left-hand limit is 1. And then same kind of deal for our right-hand limit. So we have LIM, limit, our function g of x, and for the right-hand limit, we're using values that are slightly bigger than 2. So they're added on a little bit extra. So for the right-hand limit, we're looking at x values that are over here, and we're watching what happens as we move along our curve as these x values get closer and closer to 2. So as these x's get closer and closer to 2, we're taking our steps along the curve, And again, we say the value of this limit then is the y-coordinate for whatever point we're approaching. So in this case, the y-coordinate there is 2. So you can see the y-coordinate, or the left-hand limit is the y-coordinate of whatever point we're approaching over there on the left. And the x value is whatever, where the input is getting closer to. So x is approaching 2. So you can kind of see the 2's match up there. And then for our right-hand limit, again, it's the right-hand limit. The value of our limit here is the y-coordinate of whatever point we're approaching. So this is kind of the idea. So what limits are going to allow for us is they're going to give us a way to kind of imagine moving along the curve. You want to think of limits as sort of small movements along the curve. So we're interested in what's going on, in this case, at x equals 2, but we're interested not specifically just at x equals 2. We're interested in what's going around kind of in this whole area here. So we want to go a little bit to the left, see what's happening over there. What point does it look like we're approaching? We want to go a little bit to the right, see, over there, what point does it look like we're approaching as x gets closer and closer to 2. And then, just to make note here, this function is defined at x equals 2. So this graph So in this case, g of 2, what would be the value for g of 2? Well, if I'm looking directly at x equals 2, so now we're kind of zeroing in on that one specific x value, that one input, and we're looking just specifically what's going on at x equals 2 here. I read up. This point is an open dot, so it's kind of missing from our graph. So I keep looking, and then I find a filled in point that's enlarged to show detail. And the y-coordinate for that point is 2. So the value of our function would be 2. So again, with these open dots, or these filled in dots and these open dots, don't be thrown that we just make them bigger so that we can see what's going on. But you want to think of the entire curve. We could graph this entire curve with these big dots, and then they would just blur together. So to really make things stand out, we just kind of, if there's endpoints, we kind of make them larger just so we can see what's going on. All right, so we're going to continue on with this in class. So give the preparation problem a try, and bring your solution with you to class, and then we'll work on some more problems then as well. All right, so we'll see you then. Bye-bye.